From ContainerDays Hamburg, this video is proudly presented by DuxIT.
Each time I go to a conference and I'm about to do a talk about KRO, I never really understand why there is so much interest in this project. Because objectively, KRO is a very, very tiny part of Kubernetes as a project. But last time I did this talk was early this month in India, KubeCon India. And I had a room of 500 people. There was 750 people in the room. And there was people sitting right in front of me. And I was like, why are you all care about it? It's not even production ready, and people care about it. But anyway, we're here, so let's talk about this. What is KRO? Hi, everyone. My name is Abdel. I'm a developer advocate at Google. I'm based in Sweden, Stockholm, originally from Morocco, if you care about knowing why my name is Abdel. And I do this thing called the Kubernetes Podcast by Google. I don't know if there are any listeners. Oh, a few, OK. I will give the rest of you 5 minutes for subconjecting. So I work on Kubernetes mostly and containers. And my background is in infrastructure. I came from the data center world. I worked in data centers for a very long time. So I do fundamentally understand what Kubernetes is and what problems it solves. And I am going to preface my session by saying that, sorry for everyone in the room who is a big fan, I am not a fan of Terraform, and I am not a fan of Pulumi. I do not like infrastructure as code at all. And I am a huge fan of YAML. I know that there is a lot of debates about this. I know that a lot of people hate YAML. I don't. So for me, KRO represents the solution to the Terraform problem. So I'm going to walk all of us through some fundamentals so we can get to understand what KRO is and what it does. Starting with the fundamental of how Kubernetes work. I think this should not be new to most of you. If this is the first time you see a diagram like this, you are in the wrong conference. So Kubernetes is what? It's basically a system composed of two components, a control plane and a worker plane. The control plane is the brain of the system. That's where you tell Kubernetes what to do. The data plane is where things happen. You, as a developer, user, platform engineer, DevOps engineer, whatever you want to call yourself, you're running containers. Containers runs inside a thing called a pod. The pod runs on a node, but you don't really tell Kubernetes what to do or how to do what it does. You tell Kubernetes, I want something to happen. We call that in English intent. You express your intent in the form of YAML, and then Kubernetes make that intent happen. One of the best ways that have been described to me in the podcast to think about Kubernetes is that Kubernetes is a promise machine. What does a promise machine do? It promises you that something will happen eventually. So you tell it, I want this thing to exist, and then at some point in the future, it will happen. A different way to think about it is that Kubernetes is an eventually consistent system. Part of the control plane are multiple components, but these are the core components that in a control plane Kubernetes has, right? The API server, the thing that you talk to using kubectl or kubectl or kubecontrol or however you want to call it, but there is only one correct way of saying it. Let's all say it together, kubectl. Good, right. Then you have this thing called controllers or operators. So the controllers are the things that execute stuff for you. Then you have etcd, the database, and the scheduler. Three of the main core philosophies of Kubernetes is that it's declarative. You don't write code, you write configuration for Kubernetes. It is extensible, which means you can take Kubernetes as a system and add things to it to make it do things it was not initially designed to do. Right? Kubernetes is designed to run apps. You can make it cook eggs for you if you want. You can eventually write a piece of controller, run it inside of Kubernetes that you wake up in the morning and you do kubectl create toast, and then it triggers the toaster in your home to toast bread for you for breakfast. You can make it do that, right? And it's universal, which means there is only one way and one way only to configure Kubernetes, which is YAML, right? We call this commonly KRM, Kubernetes Resource Model. Everything in Kubernetes is considered a resource because Kubernetes is based on the idea of HTTPS. In HTTPS or REST, you have two main working methodologies, which are operations and resources. You define a resource, that's the payload, and then you tell Kubernetes to execute an operation on the resource. Put, if you want to push the resource toward Kubernetes. Get, if you want to get the resource from Kubernetes, et cetera, et cetera. So this basically means that everything that you declare toward Kubernetes is a resource from your perspective. So a resource could be a pod, It could be a config map, it could be a secret, or could be a toast, right? This is typically how a resource looks like. Again, this shouldn't be a surprise for most of you. I'm sorry if I'm boring you with the details, but this is important. A resource is just a set of YAML files. YAML describes what the resource is, and resource is essentially a set of fields and values, right? This basically means that when you are interacting with the Kubernetes cluster, you are creating or managing resources, but you could also create custom resources. We call those CRDs, custom resource definition. So beyond the resources that Kubernetes knows natively, pod, Kubernetes, config map, secrets, persistent volume claim, blah, 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 you can also tell Kubernetes to manage new resources, new types of resources, a car, a toast, a fridge, something, a PC, a computer, a server, whatever. The way you do that is that you create what we call a CRD, a custom resource definition. And the custom resource definition is a way for you to tell Kubernetes a new type of resource to manage. Now, CRDs on their own are not very useful, because just creating CRDs means that you are just going to fill up the database with new things. In order to make resources or CRDs useful, you have to create what we call controllers. The controllers is the piece of code that will implement the custom logic for the CRD. So let's say, for example, that you are defining a CRD, which is the database. You tell Kubernetes there is a new resource called database, and then you create a controller that listens to this kind of resources, and then it will, so the controller will be installed, it will talk to the API server and tell the API server, whenever there is a new resource called database created, please tell me, because I know how to make that thing happen, the promise part of the promise machine. So this is how you define a custom resource definition. This is a very short one. In this particular example, our CRD is called counters. It has a bunch of fields which we don't care about. Let's just go all the way until the spec. And in the spec, we have only one field called value, and the type of that field is integer. Now, in order to make this useful, you have to write a controller, as I said. And then later on, you can create an object like this. This is what you see as a user. Counter, name, value, 42. What happens in this particular case is that you are executing a put command toward the API server to push that YAML file toward the API server. And then a controller will listen to that, grab the resource that you created, and then go and do something with it, execute a piece of code to do something with it, right? So controllers are essentially the piece of component that bridges the gap between custom resource definition inside Kubernetes and the external world. So that's the thing that will create a database, create a bucket, create an object, toast your bread, do something, right? This basically, as a concept, as a fundamental concept, is the core of how most of Kubernetes-driven infrastructure management works. Most cloud providers, a while ago, created a bunch of controllers and a bunch of CRDs that allows you to use Kubernetes to manage the resources of that particular cloud provider. These are the main three ones of the main three cloud providers. I assume that other cloud providers have their own things, but basically in Google, we call them KCC, AWS call them ACK, and Azure call them ASO. So KCC, ACK, ASO are all controllers, and when you install them, they install a bunch of resources or custom resource definitions, CRDs, inside your cluster that allows you to create an object, let's say S3 bucket, object type or kind S3 bucket, name my bucket, region, Europe West 1, and then the ACK controller of AWS will listen to that when you create the object and then go and create that resource for you, create the piece of bucket or the piece of infrastructure for you. One of the early projects to leverage this ability of Kubernetes is called Crossplane. So Crossplane is open source. And it is a project that basically was created to leverage the custom resource definition and KRM, Kubernetes Resource Model, to allow you to create cloud resources using Kubernetes itself. So it comes in two formats. You have Crossplane open source, which you can install yourself. And then you have a single Kubernetes cluster where you're engineers are pushing resources that get created later on. And then they have a managed version, right? And then every single cloud provider, Google, AWS, Azure, they have their own version. We have KCC managed, there is ACK managed, there is ACO managed. I think the AWS one is part of CDK, et cetera, et cetera. So basically, this means that there are essentially two kind of personas in this kind of model. One persona is the platform admin. That's the person that will create a Kubernetes cluster, install the CRDs, install the controllers, and then make that available to the developers. And then the developers come in later and use KRM to manage the resources. So these are just two random examples of how this happens. You are a developer. You create a Cloud SQL interface, which then generates a MySQL database or a bucket or whatever, and then the controller will go and create those resources for you. Now, one of the main problems, I would say, with CRDs and operators is that they are very, very hard to manage. It's very easy to actually DDoS a cluster with CRDs and with operators, because you just can install too many operators, create too many resources, fill up etcd, end up with a situation where the controllers are just like constantly pulling information from the API server, and then the API server go down. And then managing them is quite easy because it's code, right? So you have to manage it, secure it, patch it, do all the stuff that you need to do as part of your operations. And that's why KRO was created. KRO was created as a way to help people natively manage resources and CRDs inside Kubernetes without requiring to install extra stuff. Now, there is a huge caveat, which is the fact that to use KRO, you have to install extra stuff to start with. And that kind of defeats the purpose of my definition. But the goal of KRO is to be as close or as natively available in Kubernetes as possible. I think that the hope of KRO, I haven't confirmed this theory, but I think that the hope of KRO is that KRO will become part of the API server, which means when you install Kubernetes, KRO is available out of the box. So you don't have to install extra stuff. So how does it work? Well, let's take a very simple example. Here I have a Visual Studio Code, which I think you all know what it is. And I have a very simple example I can show you here. So let's say, for example, that you are trying to create, deploy an application, right, in Kubernetes. Is this visible, by the way? Is it good? Cool. All right. So you're trying to deploy an application inside Kubernetes. So to deploy an application inside Kubernetes, you need basically three things to make the application useful: a deployment, right, a service, and an ingress, or some sort of load balancer. So your deployment looks like this, right? Your service looks like this, and then your ingress looks like this. Optionally, you might need a config map. You might need a secret, a persistent volume claim, et cetera, et cetera. What I'm trying to get into here is that this file, this YAML file, which is 78 lines of code, could get even longer and longer and longer. Now, I know that some people who are very, very huge fans of Helm might argue that this can be actually templatized with Helm, and Helm can make things easier, which I'm not arguing against. Going back to how I started, I also don't like Helm. So how would you make this simple? Let's take a much larger example. Let's say that you are a WordPress provider. Your business provides WordPress as a service, which means your users or your customers just click a button to deploy a WordPress website. Essentially, every single deployment you are going to execute is the same. All your WordPress installations are the same to start with. You are just taking the same exact YAML file, duplicating it for every single customer, which means that this 78 lines of code file will exist in multiple copies, right? Customer 1, customer 2, customer 3, customer 4, blah, blah, blah. The name might be different. Some configuration settings might be different, but the same, more or less, file will exist in multiple copies. So how does KRO help us? So KRO introduces this concept of resource graph definition. So a resource graph definition allows you to do two things. One is expose an interface that the user gets to define. And then two, define what happens when an instance or a copy of that RGD is created. So in any RGD, you will have basically two sections. There is a spec section, which has a schema. In the schema, you are defining the type of the object. So the type of the resource, in this particular case, we're calling it application, the API version, obviously, and then the spec of that resource, which is essentially the interface, the thing that gets exposed to users. In this particular case, we're saying that for this particular RGD, resource graph definition of type application, we have 3 fields. A name, which is a string, an image format, or an image URL, which is a string, and it has a default value. The default value is nginx, which means if users don't define it, it will default to nginx, right? And then an ingress of type Boolean, and it defaults to false. So if we don't define it, there will be no ingress created. If we define it, there will be an ingress created. All of these fields in the spec part of the RGD are actually variables, which means we can refer back to them using a very particular schema. One interesting thing that to talk about here, and I'm going to show you another example, is that fields can be, I think, of 4 or 5 types, if I'm not mistaken. It's like integer, Boolean, string, list, and array. And they can be nested, which means I can actually create a nesting here, which is ingress. Inside ingress, I have enabled, and inside enabled, I have type. And I can say, I can say something like type is string, and it will default to, let's say, internal, right? So I can keep nesting them as I see fit. I don't really recommend it because it becomes very hard to read, but you can do that eventually. Then I have the status field, which I'm going to get back to in a second. Then there is the second part of my RGD, which is the resources. Essentially, the resources defines what are the objects that will get created when an instance of my resource graph definition is created. In this particular case, I have a deployment, and this is where we go back to that idea that fields inside the spec part of the resource graph definition can be used as a variable. To refer to a variable, we use the $sign, and then we just refer to it with schema.spec.name. If I want to refer to the ingress object, that would be, where is the ingress object? Yeah, schema.spec.ingress.enabled. There is also something called an if statement, which essentially, if you have a Boolean value, true or false, you can add this thing called include when, and essentially it will only include the object when the value is set to true. So in this particular case, my ingress object will only be created if ingress in the resource graph definition part have been set to true. So now that I have created this, I can basically push it to the cluster. I have already created, I have already installed KRO. It gets installed in a namespace called KRO system. And inside that namespace, there is actually just one pod. Sorry, it's not KRO system, it's KRO. And then inside of it, there is only one pod. That's the controller. That's the KRO controller. There is also like resource graph definitions. So if I do kubectl get CRDs, and then I grep on KRO, then I have a bunch of KRO objects that are installed for me. The resource graph definition is this one. These two, we're going to get to them in a second, but this will be created when I install the resource graph definition. This resource graph definition is called simple RGD. So I'm going to apply it to the cluster. Like that. And then if I query back my CRDs, I will see that there is actually a new custom resource definition created called applications, right? So essentially, one of the things that KRO does is when you create a resource graph definition, it creates a CRD for you. It generates a CRD. Now, as I said earlier, this is not very useful because just creating the RGD or the resource graph definition doesn't do anything because there is no controllers. The goal of KRO is not to define the controllers. It's not to see or to sit or to be in the business of defining what happens when an instance of the RGD creates. The goal of KRO is just to define the RGDs, define the underlying resources. This part here of the RGD definition, the resources themselves, they should have their own controllers that does something with that particular RGD. In this particular case, we are defining Kubernetes native resources, which are deployments, service, and ingress. So Kubernetes already have a controller for them, so we don't have to do anything extra. But if you are using KRO to abstract away cloud resources management, then you have to have that particular cloud controller installed in the cluster, right? Because once an RGD is created, then there is a controller that needs to act on that particular RGD to do something with it. So now back to my example, which is to deploy a deployment, I need 3 objects. Now that I abstracted it away with KRO, I can basically make it as simple as this, which is 9 lines of code. So to deploy an instance of my Nginx, Ingress, or WordPress, or whatever example you want, instead of writing 78 lines of code or configuration file, I write 9 lines of code. So I am creating an object called application. My object is called my app. It has a name. It has Ingress enabled, and it has an image. So now let's see that in action. So if I do a kubectl get pods, okay. Let me remove this because then it will be easier. So I'm going to delete this deployment just to make it simple for us. Go back. I have, let's say that we have 0 pods, right? Nothing is created for now. So what I will do is I will just apply my instance, right? So I will go simple RGD, and then instance, and then apply that. Now that I applied it, if I query the cluster to say get application, right? Because application have been registered as a custom resource definition, it will give me an object. It's called my app, and it says it's in progress, which means that the underlying resources under that particular RGD are being created. Now that things are active, I can actually query back my cluster and say, give me, are there any pods? Yes, there are 3 pods, right? Because in the RGD definition, in the resource section, I said that whenever an object of type application gets created, it will generate a deployment, and there are 3 replicas for that deployment, right? Then if I query my services, I should have a service somewhere. So I do have a service called my app service, right? And then if I query my ingresses, I should also have an ingress called my app ingress, right? So essentially, I took a potentially very long YAML file. I abstracted it away behind one resource graph definition, and then I can create as many instances of that particular resource graph definition as I want. Now, this is arguably a very simple example. A much more complex example could be things like this, for example. Let's say I want to create an object called a web app, and in that object, I have multiple underlying objects, which could be a combination of Kubernetes native objects, but also cloud-specific objects. So my application is a deployment, a service, an ingress, a Cloud SQL database, a bucket, a pub subtopic, a load balancer, whatever, you name it, like a monitoring configuration, a login configuration, blah, blah, blah. So I can define all of that in my RGD, which is what you see on the left. So I have a deployment, a service, a Prometheus configuration, a service account, a cloud service account, a cloud storage bucket, a Cloud SQL. These are Google-specific examples, but all cloud providers have this kind of objects. IAM policies, PubSub, et cetera, et cetera. So I only have to define this once as a platform engineer, DevOps engineer, and then my developers can instantiate or create instances of this web app RGD, which then will trigger the creation of all the underlying objects. What gets created when an instance of my RGD is defined could be a combination of Kubernetes native resources and then external resources. So the Kubernetes native resources will be handled by the Kubernetes native controllers. External resources should be handled by external controllers. In the case of Google, it will be KCC. In the case of AWS, it will be ACK. In the case of Azure, it will be ASO. So part of what you have to do as a DevOps/platform engineer is you have to install those controllers as well and make sure that they work, because there is an authentication piece. A controller has to be able to authenticate to the API of the cloud provider to be able to create the resources. I'm going to jump ahead to one other example. Last time I did this talk, one of the questions we got, or I got personally, was, can we actually define in the RGD what are the allowed values? So I don't want people to choose any random, well, this is not the right example, but say, I don't want people to define any random value inside my ingress name. It has to be a list or a type of object. So I actually created a very simple example yesterday, which is this. So you can do it by essentially defining your field as a string and then creating an enum. And then the enum says what are the allowed values, and this can have also a default value. In this particular example, I choose machine type, which is a very relevant example. Let's say that you as a platform engineer do not want to allow your developers to create any type of machines. You want them to only create very, very specific type of machine shapes for cost-saving reasons. Well, you can define those as a list. So in this particular case, I allow N1 standard 2, N1 standard 4, and it defaults to N1 standard 1, 2 if the user doesn't define a value. N1 standard 2, N1 standard 4, those are very specific Google examples. Again, you can define whatever you want, right? This also can be very useful for security reasons. I know that's a huge part of doing AWS resource management is defining like IAMs, I think, the identity, whatever they call the security IDs. So you don't want people to necessarily define any value they want. You have to give them you want to give them very, very specific values that they can choose from. This also can be used for firewall rules. You don't want people to define any firewall rule. Specifically, you don't want people to create a firewall rule which is 0.0.0.0/0, right? You want them to choose from a specific list. So I can show you this in action. I called it Playground. I think I have it already installed. Let me double check 1 second. And I think I am gonna get very close to my end time. So I'm gonna stop here after this example and then get any questions. What? Come on. Oh. Give me 1 second. Hopefully, I'm not going to show you my password. All right, good. Now it works, hopefully. So I already created my my object. So if I query get playground, because the object is called playground, I already have it. So now let's see that I want to apply this object here. So create an instance of my playground object. So I'm just going to apply this one. It's called playground RGD. So this one should work because the value of machine type is within the list of allowed values. So N1 standard 2. So this should be created. And yes, it was. But now if I comment this one out and then choose to create this one here, this will not be allowed because obviously sorry. This will not work because I have a value here which is not in the list. So I get an unsupported value N1 standard 8, and then it tells me I can only create N1 standard 2 and N1 standard 4. So this is just an example of the kind of field types and what you can do with them. So enum or array is part of what you can do there. So I'm going to skip ahead. Few things to keep in mind, and then I'm open to questions. KRO is experimental. It's not stable. It's not version 1. It's version 0.4.1, which is the latest version. So keep that in mind. Experiment with it. I wouldn't put it in production. KRO is not the answer to all the questions. You will have to bind it with a cloud-specific resource thing to make it useful. KCC for Google, ACK or ASO for the other cloud providers. And that's all I have. I hope it was useful. I'm going to stop here. And if you have any questions, I'm open to answer them. Thank you so much.
So yeah, we have two from Chris. Can we deploy multiple versions of the same RGD into one staging cluster so we can implement a dev workflow for the resource graph definition itself, or do we need separate clusters?
You can do it. You just have to call them different names. And then also make them create different kinds. So if you create RGD called RGD1, and then in the spec, it creates an object called application. And then you create RGD2, they will collide with each other. They will be conflicting. So you have just to version the names of the RGDs and then the name of the kind or the resource kind they generate. But yes, you can do it.
Next to the next question, how far away from production readiness is KRO right now?
Yes. So that's a question that comes up very often. There was a hope to make this production ready by the end of the year. Unfortunately, we lost the product manager who was working on this inside of Google. So we are actually hiring a new product manager. I would say probably end of the year, if not hopefully early next year. But it's within the next 6 months, 9 months. Don't hold me on this. I might be completely wrong. So I write very, very little code. I am more like talking about this as a potential new thing coming to Kubernetes. I'm not one of the maintainers. But the repository is very active.
I think we have a few questions about if KRO is Helm or cross-plane killer, or how do they compete to each other?
So if you go on YouTube and look for is KRO a crossplane killer, there will be a video by Victor, who works for crossplane, saying that this is the next cross, or works for Outbound, which is one of the crossplane people. I would say no. Actually, one of the questions that came up, or one of the experiments I am running, I haven't finished a demo yet, but I'm working with this. Last time I was in KubeCon India and this talk, I ended up having a long conversation with someone, and we kind of figured out actually that you could templatize KRO using Helm. So you could use Helm as a way to create KRO templates, because Helm is just a templatization platform. So you could combine Helm and KRO. Is it going to be a cross-plane killer? Potentially, maybe. Like at some point, probably you wouldn't need, if KRO is available in Kubernetes out of the box, you don't need to install extra things. So.
Why does KRO spec not use Open API for the spec?
That's a very good question. I don't know. That's a good question to ask actually on GitHub. Just open an issue and ask them why are you not respecting the Open API spec. I think they're trying to make it simple. Open API spec is quite convoluted, quite complex.
Support KRO different versions of RGDs at the same time?
I think we answered this question. Yes, you can. You just need to call them different names, essentially. So.
Can I dynamically create resources?
Can I dynamically create resources based on user inputs? Example for loop. No, but it's actually a feature request I opened. I did particularly ask this question about creating some support for loops. And one of the use cases was creating like a cluster of objects. Let's say you want to create like 10 virtual machines, 20 virtual machines, and they all are the same shape, the same configuration, the same everything. They just call them different names. So I opened, if you go to the GitHub, you'll find an open feature that I created asking for support for loops. So the answer is no, but hopefully it will come at some point.
Your podcast is very good.
Thank you so much.
What about secret injections of certificates and keys? Should we use something other than the CRD, for example, secret provisioner, or adding logic to RGD?
Secret injection of certificates and keys. Well, I would use the secret manager, right? Like the standard secret manager in Kubernetes. External secrets is a very good project. I know that it has some problems with maintainers and maintenance and stuff like that. And there are some questions, so open questions about that. But I wouldn't trust CRDs, generally speaking, with secrets or keys. I would just use an external secret manager.
And last two questions, maybe you can answer them together. What happens when changing an existing definition, and what happens when the application is deleted?
In your example, will it? So yeah, that's a very good question. When you create an RGD, and then you create instances based on that RGD, the instances are frozen in time, which means that the instances you create are based off the RGD you defined in the first place. If you change the RGD later, like adding more fields, changing default values, the existing objects will not be touched. But if you delete the existing object and create them again, then they will follow the new schema. So yeah, basically, it's a sort of versioning. If you create a new version of the RGD, it will only impact the new objects created out of that RGD, not the existing ones. What happens when the application is deleted? The application, you mean the RGD? If you mean the RGD, then deleting the RGD will delete the resources. Deleting the RGD will delete the existing objects, essentially. So there is like a kind of a relationship there.
Okay, I think it's similar to previous one. You can answer one question if a short one. We have still 1 minute. Is there a limit on what controllers can do? Maybe this one?
No, I mean, controllers can do controllers things. I don't think there is a limit to what controllers can do. Like, the way controllers work and the way KRO works are completely disconnected from each other. The only relationship is that the fact that KRO allows you to define an RGD that defines an object that if there is a controller for it, it will be triggered when that object is created. So there is basically no relationship between the two. But as I said earlier, in order to make KRO useful, you will have to have the controller that acts on the objects that are created by the RGD or by KRO.
Thank you.
Thank you so much. I'm going to be around if you have any more questions.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.